Okay. Now comes some interesting the filter bank elements and some interesting results. I hope you will enjoy this part of the discussion. So, we are now shifting gears and going to be focusing for the several a significant portion of the coming lectures on filter banks, but again we will do it in pieces so that you are able to put it together like a big jigsaw puzzle, but this is the first of those elements. So, filter banks, we already said that the basic operation that we will get is through a modulation, right, which will shift this. If this is H0 of z, this is H1 of z, and we said that H1 of z is H0 of zW. This is a M channel filter bank. So, W is actually equal to Wm, which is equal to e power minus j 2 pi over m. So, this is actually H0 e of j omega minus 2 pi over m. Okay, this is the basic definition of the shifted filters. So, if this is minus pi over m to pi over m, the center frequency for the first filter is 2 pi over m, the second center frequency for the second filter will be 4 pi over m, and so on. Okay. So, let us quickly get that out of the way. This would be 4 pi over m and so on, and the last one will be the 2 pi minus 2 pi over m. Okay. So, that is the basic framework. Now, here is where what we have studied with multirate comes into play in a very elegant way, and this is where we will take go a little slow, but it is very important that we understand or follow the thought process. So, H0 of z, if I were to write it as a polyphase decomposition, type 1 polyphase decomposition. So, then this can be written as summation L equal to 0 to m minus 1 z power minus L E L Z M. This is type 1 polyphase decomposition. We are now quite familiar with this. We are just going to look at this expression. Now, from this we will derive H1 of z, we will derive H2 of z all the way to Hm minus 1 of z. These are nothing but H0 of zW. Again, W refers to W subscript m. This one is H0 of zW squared. The last filter is H0 of zW m minus 1. Okay. Now, even when we do the first filter itself, you will start to see some very interesting patterns emerging. Let us take a closer look. So, basically wherever there is z, replace it with zW. So, this expression would become L equal to 0 to m minus 1, zW raised to the power minus L E L zW raised to the power m, correct. Wherever there was z, I have replaced it with zW to get my first filter. Okay. Now, please look at what is within the bracket. This one, if I simplify, W raised to the power m will be equal to 1. So, this is nothing but z raised to the power m. Okay. First observation. So, this one can be written in the following way. This can be written as summation L equal to 0 to m minus 1 W minus L, and then I am going to group the terms inside z minus L E L z raised to the power m. Okay. Now, if you were to look at any arbitrary filter Hk of z, this would be H0 of zWk, k is in the range 1 through m minus 1, and all of these would satisfy the following structure. this would be L equal to 0 to m minus 1 z w k raised to the power minus L E L z w k raised to the power m. Okay. Now, looking at what is within the bracket, w k raised to the power m is also equal to 1. So, this is nothing but z power m. So, we can now write this in the following way: summation L is equal to 0 to m minus 1 w minus k L z power minus L E L z power m. If there is a input x of z, what will be the output? So, if the input is x of z and the output, let us say that I call the output of h k of z as x k of z. X k of z is h k of z times x of z. So, basically it would be this expression multiplied by x of z. Now, if you are go back and review your basic DSP principles of when we write a input output relationship in terms of a transfer function, and carefully look at this structure that we have obtained, what you will find is that h naught through h m minus 1, there are m such outputs. So, basically you will have x naught to x m minus 1, so many outputs are there. Each of these requires you to process x of z by the same set z power minus L E L z power m, and once you have processed with that, then you are multiplying it by some phase terms and then taking a summation. Okay, because if you notice x of z and this set where L equal to 0 to m minus 1 happens for all of them. So, if you were to if you were asked to implement this in a form, you will get a very interesting structure. So, the structure that implements that, if you were to derive it, I am sure if you by spending time you will definitely be able to do it. Let me just suggest that how we want to do that. E naught z power m, z inverse E1 z power m dot dot dot, the last one is z inverse E m minus 1 z power m. Okay. So, x of z processed by each of these. So, this is x of z processed by each of these filters. Is that correct? Is it consistent with what we saw in the previous expression? Let us verify. X of z multiplied by z power minus z power 0 E 0 of z m, second one will be z power minus 1 E 1 of z m. That is exactly what we get here. X of z E naught of z m, x of z z inverse E 1 of z m, x of z z power m minus 1 E of m minus 1 of z. Now, what did we do to these outputs? You multiplied it by w minus k L. Okay, depending upon k. Supposing it was the k equal to 0, what was it? Just added all of them together. Then, so if you look at it carefully, these if you have the powers of w, that would have been the DFT matrix. This is the IDFT matrix. So, basically what you have here is a well known matrix. It is the DFT matrix, actually just conjugated, but it is a symmetric matrix. So, therefore, transpose conjugate is the same. By the way, anytime we have a matrix, a dagger symbol means that you do transposition followed by conjugation, okay, transpose conjugate. Okay. So, that is the notation. Anytime we deal with complex matrices, constant matrices, the dagger symbol represents that. So, basically this is a like the IDFT matrix. The IDFT matrix will have a scale factor, but other than that, this is the structure. Now, notice how efficient this structure is to get the output of m filter banks which are shifted by as we have specified, where the filters have been are shifted by multiples of 2 pi over m, that is closely linked to the DFT coefficient. Now, if I use polyphase decomposition, I will get z power m. That means all of these DFT coefficients kind of get mapped back to 1. So, therefore, the expressions become very simple and then we get this expression. Now, we also had another result I want you to keep in mind. When you have a signal which is band limited to 2 pi over m, anywhere in the 0 to 2 pi range, you can downsample by a factor of 2m without aliasing. So, which means that in the general case you can also do the following: you can downsample by m each of these branches. Each of these branches can be downsampled by a factor of m without aliasing. Okay. Now, go back and apply one more principle, interconnection of multirate blocks, adders, multipliers. When you have the decimators, they can move to the other side of the linear blocks. So, basically the DFT matrix consists of multipliers and adders. So, this downsampling by a factor of m can actually move to the left of the, so you can actually move the downsamplers to this side. Now, noble identity, one more time you do it. So, what do? You actually have x of n coming in. So, now you can replace this with x of n. You have the demultiplexer, basically the stream, input stream is getting demultiplexed into parallel streams, each of them being processed by a sub filter. This is each of these are polyphase components, so their length is much smaller than the original prototype filter. And once you do that, you do a inverse DFT, same as the DFT, you can use a fast algorithm, fast transform to implement this. So, you will get your outputs, m outputs with very high efficiency. So, basically what we can write down here is that this turns out to be a very efficient implementation, we have utilized several of the tools that we have developed, the interconnection of multirate blocks, the noble identities, and of course the shifting of the filters, the what happens when you have the DFT coefficient raised to the power m. All of those results have kind of come together. So, maybe this is a structure that you must spend some amount of time and either redrawing or analyzing and applying. So, you get a very efficient implementation, very low computational complexity, because you are using the DFT, you are using the polyphase, you have kind of taken advantage all around, and the efficiency comes because we have used the advantages of polyphase to the maximum. Advantage of polyphase decomposition, that is a result from multirate DSP, along with the computational advantages we can get using the fast transforms. So, IDFT will be implemented using the fast transforms, which you have studied in DFT, so in DSP. So, therefore, you can get very efficient structures for this particular. Okay, now I am glad you asked the question. The question is what role do these downsamplers play? If I did not do this downsampling, what would be my input sampling rate? If my input sampling rate was n0, what would be the output sampling rate at this point? It would still be n0, it would be n0 here, it would be n0 here. Effectively, I would have got m times n0 as my sampling rate on after I have done the filtering. Each of the filters produces, which is very, which is quite obvious, because I take a input signal, I filter it, I get an output, input and output are the same rate, and I have m such filters. So, at the output. Now, if you want to have the most efficient in terms of storage or processing, do I need to retain this at n0? The answer turns out to be no, because if this was a band limited filter, I know I can downsample and recover the original signal. So, this one becomes n0 by m, all of these become n0 by m, and the effective sampling rate at the output, if I do the downsampling, actually remains at n naught. So, this is more for storage or for efficient processing. Again, you need not do it, but if you do it, you get the maximum advantage of the polyphase structure, and one of the reasons why we would do it is because you actually can do the downsampling by a factor of m, retaining the input output sampling sample rate at the same level without loss of information. Okay, so now we need to spend a little bit of time on understanding the properties of the DFT matrix. I would like you to spend some effort on that, and we will quickly touch upon that. I am sure you must have you would probably have looked at it in other contexts, but let me just make sure that there is an opportunity for us to at least discuss that. So, properties of the DFT matrix. So, properties of the DFT / IDFT matrices. So, in case you are not very familiar with this, I would say just request you to brush up on linear algebra and some of the basic definitions that we would like to discuss here. So, W subscript n is e power minus j 2 pi over n. This multiplicative factor would come when we do an n point DFT or IDFT. So, n point DFT would basically have the following matrix. First row will be all ones, second row will be 1 Wn squared dot Wn n minus 1. Second row first row, second row, third row would be Wn squared Wn 4 dot Wn 2 times n minus 1, and if you come down the list, the last row would be Wn raised to the power n minus 1, Wn raised to the power 2 times n minus 1, and the last term would be Wn raised to the power of n minus 1 into n minus 1. Okay, again exactly what you would have studied in DFT, IDFT relationships. So, this is what we refer to as the DFT equation. X subscript k or x within brackets k, this is the same as x of k. This can be written as summation, no, this is not a matrix, this is a scalar. Okay, this is summation n equal to 0 to n minus 1, it is an n point DFT, x of n Wn nk or kn. Now, if you remember, this was what we observed to say that the filter bank actually comes from a DFT matrix, because this is how you compute the DFT coefficient. You take the inputs and you multiply it by these phase terms, and then you sum them up to get the expressions that we are interested in. So, the W matrix consists of entries which are Wn raised to the power kn, where Wn is the e power minus j 2 pi over n. So, the element of the nth column and the kth row, k represents the row index, n represents the column index, and basically what we have is this will become e power minus j 2 pi over n times nk. And I think it is easy to see that this is a symmetric matrix, because if you do W equal to W transpose, the row index and the column index will interchange, and basically it just says that Wn nk is the same as Wn kn. So, these are basically it is a symmetric matrix. So, okay, but it is more than a symmetric matrix. For the reason that if this equation can be written in the following way, x is equal to w times lowercase x is lowercase x representing, let us say, time domain. So, this is the n cross n matrix. Let me write the dimensions in a different color. This would be an n cross 1, this would be an n cross n, and the input vector is again an n 1 cross n cross 1. Okay. So, basically that is the DFT equation in matrix form. So, this and this are identical. So, equation 1 and 2 are identical, right. One is writing it in matrix form, the other one is expressing it as a summation. Okay. So, given this result, we can also verify, I am sure you can verify the following result: W dagger, that means transpose conjugate. Transpose will be the same thing, basically multiply the conjugate. If you multiply W dagger times W, what you will get is n times the identity matrix, and you can use the basically the roots of properties of the roots of unity to verify that, and I am sure you would have done it already in the context of the DFT. So, this result basically tells us that the inverse DFT, so this is the inverse DFT. Inverse DFT is equal to W dagger divided by 1 over n, and which is what we have in the IDFT equation. You will have a 1 over n term, and why did that 1 over n term come? Because W dagger W gives you a scale factor, you basically are taking care of the scale factor. Okay. Now, once you study these properties, you can just note down that the following observations: if a square matrix, if any square matrix satisfies the following property, n by n matrix satisfies the following condition, which is U dagger U is equal to a constant times the identity matrix, okay, for some c greater than 0, some scale factor c, then U is said to be unitary. U is said to be unitary. Unitary matrices have got many interesting properties. I will just mention the one that is most important to us, the property that every pair of rows or pairs of columns. So, this is the property that is visible right from the basic equation. Every pair of columns or rows and rows are mutually orthogonal. This is a powerful result, mutually orthogonal. Okay. Now, how does it manifest itself? If you write down the columns as C1, C2 up to Cn, these are column matrices, and what does the basic result say? U transpose conjugate. So, what you will get is C1 column, you do transpose conjugate, it becomes a row vector, C2 dagger, Cn dagger. Now, C1 dagger times C1 becomes identity or some scale factor. C1 times C2 is 0. So, basically you can see how this will manifest itself as some constant times the identity matrix. Okay, so, and similarly you can show it for the rows as well. So, the DFT matrix is a very rich in symmetry. It has got lots of very interesting properties, but as far as we are concerned, it is a matrix that we would like to leverage for our multirate structures. Okay. But I want you to maybe do the following exercise. Can you take a look at this structure and replace this with the DFT matrix, and then think about what is happening, what is the what change is happening. Okay. So, I would like you to just, again, it is not a very difficult task, but something for you to think about, because this is now going to tell us, going to give us a lot of insight into the structures that we are going to be developing, and this is also going to tell us, and what you will find is that these outputs just get cyclically shifted. That is all. There is not nothing very profound happening, but this is what is going to teach give us a lot of insights into the use of multirate or the DFT as a spectral analysis tool. But this is very important, that you see the relationships between the shifted filters. When you use the IDFT, they shifted in this direction. Now, when you use the DFT, you will find that the shift happens on the negative side, but in case you do look at it, we will pick it up from here in the next class and develop it. Thank you.